An electrical machine is a device that can convert either mechanical energy to electrical energy or electrical energy to mechanical energy. When such a device is used to convert mechanical energy to electrical energy, it's called a generator. When it's required to convert electrical energy to mechanical energy, it is called a motor. In this course, we are going to look at both generators and motors, and basically we're going to call them rotating machinery. We're going to start off with an introduction and review of machinery principles, including what is meant by the cross product and dot product of vectors, torque and circular motion, and torque power measurements and the rate at which work is done. We're also going to look at instantaneous and average power in rotating systems, and we'll then have a quick review of electrical magnetism. We start off by firstly looking at linear DC machines, which are the simplest type of DC machines, so that we can have a better understanding of the equations and the idiosyncrasies that are involved with DC machines. We then move on to rotating machines, including motors and generators, and such devices as commutators that are used for DC motors and generators. Next, we will look at AC machines. Fundamentally, the principles of AC machines are very simple, but unfortunately they are somewhat obscured by the complicated construction of real machines. In this chapter, we will concentrate on the fundamental principles of the two major classes of AC machines, synchronous machines and induction machines. The chapter starts off by looking at induced voltages in a rotating single loop of wire, developing the equations for torque induced in a current carrying loop, and is then expanded to slightly more complex induction motors, including three-phase motors with a revolving magnetic field. The course then spends some time looking at single-phase induction motors. As the name suggests, these motors are used on single-phase supplies. Single-phase motors are the most familiar of all electric motors because they are extensively used in home appliances, shops, and offices. It is true that single-phase motors are less efficient than three-phase motors, but three-phase power is normally not available except in large commercial or industrial establishments. Since electric power was originally generated and distributed for use in lighting only, millions of homes were given single-phase supply. This led to the development of single-phase motors. Even where three-phase mains are present, the single-phase supply may be obtained by using only one of the three lines as a neutral. And in this chapter, the focus is on the construction and characteristics of commonly used single-phase motors. Lastly, the course will look at synchronous machines, which are principally used as alternating current generators. They supply the electric power used by all sectors of modern society: industrial, commercial, agricultural, and domestic. Synchronous generators usually operate together or in parallel, forming large power systems supplying electrical energy to the loads and to the customers. They are usually found as large units, their ratings ranging from tens to hundreds of megawatts, that convert mechanical power to AC electric power. All generators are driven by prime movers, which is the generator's source of mechanical power. The source of mechanical power may be diesel engines, a steam-driven turbine, or a water turbine, or a similar device. For high-speed machines, the prime movers are usually steam-driven turbines employing fossil or nuclear energy as the resource. Low-speed machines are often driven by hydro turbines that employ water power for generation. Smaller synchronous machines are sometimes used for private generation and as standby units, with diesel engines or gas turbines as their prime mover. In today's world, an isolated synchronous generator supplying its own load independently of other generators is very rare. Such a situation is found in only a few out-of-the-way applications, such as emergency generators. For all other generation applications, there is more than one generator operating in parallel to supply power demands by the load. This chapter on synchronous generator will study this. And in the final chapter, there will be example problems that will be solved, illustrating simple calculations involving voltage, current, and power flow in synchronous generators. And there you have it, a brief overview of what this course contains. I don't think it's a difficult course, and I think anybody who will follow it up will find it very enjoyable.